With this video, I'm starting a new series, and this series is looking at inferential methods for independent samples when we have a categorical outcome variable. We've already looked at a single sample with a categorical outcome, but what about if you have 2, 3, or more different samples, that is, representing 2, 3, or more different populations, and you're measuring every participant with a categorical outcome, obtaining categorical data. So I'm going to start in this video with the simplest possible case, and that is when we have just 2 samples, such as a control and treatment, and we're going to look at the outcomes as successes or failures. So when we have more than one sample, 2 samples, and when we have a categorical response, just 2 possible categories, that's about as simple as you can get for this sort of situation. And we're going to see how we can use the product binomial in order to be able to make inferences. So here's the setup. We wish to compare 2 populations using a dichotomous response variable. We select random samples. Now, the typical way to do this, especially if you're conducting a true experiment, is to draw one sample, but have these samples represent 2 potential populations by randomizing. That is, randomly placing each member of the sample that you draw into one of 2 conditions. But we could also draw at random from 2 existing populations, purposefully selecting a number that we choose from each of the 2 populations if we wish to compare these populations on some characteristic that can be put into one of 2 categories. The observations need to be independent of other observations. So when we collect these samples, when we draw each individual member, and then when we look at their outcomes, we want to do this independent of all the other participants in the study. I'm going to use an R package in this video. It's nplearn, which is a package that I'm working on. It's under development, but you're welcome to download it, install it, and follow along with me. It might be helpful. Here's an example. High school band teachers occasionally complain that judges in an all-state band competition are biased towards certain times of the day. Suppose that to examine this claim, a researcher randomly divided 20 students who were trying out for all-state band into 2 groups, then arranged to have tryouts for members of one group in the morning and members of the other group in the afternoon. The response of interest is success or failure in being selected for the all-state band. So here we have 2 populations being represented. They're potential populations. The population of individuals who might try out for all-state band that would try out in the morning, and those that would try out in the afternoon. By randomizing to these 2 groups, we're making sure that we don't, for example, end up with the better participants, the ones more likely to be accepted into all-state band in either the morning or afternoon, which could be a possibility if we let them choose their own tryout session. So we have 2 samples representing these 2 populations, and there are 10 in each sample, and these are formed through that randomization. The response variable is a Bernoulli event. It's success or failure in making the all-state band. Here are some example results. So I've set up a time variable indicating morning and afternoon, and an outcome variable indicating failure or success in making the all-state band. And here are some data in which you can see the morning adds up to 10, the afternoon adds up to 10, but we see that we have more successes in the morning than when we do in the afternoon for this particular sample and this particular randomization and this particular analysis. We can calculate proportions conditioned on the categories of the explanatory variable. Anytime we do this, we actually have two purposes for such statistical estimates. One is more as a descriptor than an estimate. That is, we're describing what actually happened in our sample. When we state that the success rate for the morning was 80%, that's actually what it was in our sample. But now that's only an estimate of the success rate in the larger population that is represented by this sample. That is, that potential population of individuals who might try out for All-State Band in the morning. So we've calculated here the proportions, and they're conditioned on the categories, that is, morning and afternoon. We condition on the categories of the explanatory variable, therefore the proportions add up to 1 for morning, and they also add up to 1 for afternoon. Our best estimate of the success rate for the population of students trying out for band in the morning is 0.8, and for the afternoon is 0.40. Clearly, those who tried out in the morning had a better rate of success, and we can estimate that rate difference like this. So here we are taking delta hat to be our proportion hat, that is our estimate for the morning, minus proportion hat of pi 2, our estimate for the afternoon, and the difference is 0.40. So delta hat is estimating what we could conceive of as a parameter, and that parameter would be the differences between pi 1 and pi 2 without the hats. That is what we actually would obtain in our population. So our best guess at that parameter right now, our best estimate, is 0.40, meaning that there is a 40 percentage point difference from between pi 1 and pi 2. That is, in the morning the success rate was 40%, and in the afternoon 80%. So the percentage point difference, our effect size, is 0.40. Well, we know that anytime we have an estimate, that there's going to be variability of that estimate every time we draw a new sample, or if we were to randomize again, we would get different results. So we have to take into account the variability of that estimate and do some inferences. So to prepare for that, I'll remind you what we did when we used one sample with a dichotomous response variable. We used the binomial formula. And in the binomial formula, we have two parameters: n, the sample size, and pi, the probability of success. So now here we have two samples. So we have n1 independent observations for the first sample with pi 1, an unknown probability of success, and n2, the number of observations in our second sample with pi 2, again, the unknown probability of success. So let's say that x1 is the number of successes we observe in N1 trials, and X2 is the number of successes in N2 trials. We actually can end up with two binomial formulas. That is, we can calculate the probability of success in the morning and the probability of having a certain number of successes in the afternoon. That is, the probability that we will observe some value that we set for X1 and X2. But we're interested not in those individual binomial formulas. We're interested in making inferences about delta, that is the difference in those probabilities. So to do that, we're going to use the product binomial. We have n1 observations that are not only independent of each other, but they need to be independent of the other sample. That is, the N1 observations that we said had to be independent of one another within the sample must also be independent of the N2 observations in the other sample. So if we have independence all the way around within and between these samples, then we can use a product for joint probability. So the product will give us the probability of observing a certain number of successes in X1, the first group, and observing a certain number of successes, that is X2, for the second group. If we vary the number of successes in each of our sample to include all possibilities, that is, X1, let it go from 0 to N1, X2, let it go from 0 to N2. And if we calculate delta hat for every combination of X1 and X2, we can calculate the probability of delta hat also for all those combinations. How do we calculate that probability? By using the product binomial. And by doing this for all the possible combinations, it will create the product binomial probability distribution. So let's look at an example. Let's use the sample sizes in our band tryout example, where we had N1 equals 10 and N2 equals 10. So for now, suppose the probability of success in both the morning and afternoon is 0.50. I'm going to come back to that later. But for now, let's just assume the probability of success in both the morning and afternoon is 0.50. Then what we can do is calculate this probability distribution that we see here. And what we notice in this probability distribution is we have what the values are in the number of successes in the first group, the first sample, the possible number of successes in the second sample. So we have possible number for 1, possible for 2, and we have all combinations. And then we have the difference between the proportion success for each, and that's what we're calling delta. And this is actually delta hat. This would be the possible differences we could observe. And then the absolute value of delta is if we're doing a two-tailed test that I'll talk more about in a moment, in which we would want to look at extreme values of delta regardless of whether they're negative or positive. Then we have probability for each of these, and then the cumulative probability going up and the cumulative probability down. So let's take all those possibilities, of which there are 121 different possibilities. Why? Because we have from 0 to 10 is 11 for the first sample, and 0 to 10 is 11 for the second sample, and 11 times 11, or 11 squared, is 121. So that's how we get to all these possible numbers of outcomes. Now let's do inference based on that product binomial. So a null hypothesis here is that pi 1 equals pi 2, or another way to say that is our delta equals 0. So we're hypothesizing no difference between these populations in terms of the probability of success. We begin our rejection region with the largest values of delta, finding a critical value by keeping our actual observed type 1 error rate less than our nominal value of alpha that we chose. We find the p-statistic. We could actually bypass the critical value and go right to the p-statistic by looking at the values of delta that are greater than or equal to delta hat for a one-sided upper tail test, or less than or equal to delta hat for a one-sided lower tail test. Or if we want to find the p-statistic by looking at the absolute values of delta that are greater than or equal to the absolute value of our observed delta, we can get a two-sided test. So let's try that. Let's see this in action. Again, I have set the probabilities to be 50% or 0.5 for each of our two populations. And we took samples of size 10 and 10. And we're going to use a two-sided now. So we're going to look at that absolute value of delta. So everything here is sorted on the absolute value of delta. Notice here for delta of 0.1 and negative 0.1, these both appear here as 0.1 for our values of delta. And if you recall, we actually observed a delta hat of 0.4. So if I want to get my p-value, I would go all the way down to 0.4, and I'm going to look at the upper tail. So I'm going to start here with the most extremely different from the null hypothesis value I could possibly have, and that's when delta equals 1. Remember, our null hypothesis is that delta equals 0. So taking the absolute value of delta equals 1, those would be the two values that first go into our rejection region, and then 0.9 and so forth. We had a delta of 0.4, so I'm putting in all the 0.4s I'm going to put in for calculating my p-statistic, which means I need to take this one right here, and I see that it has a p-value of 0.115. So that's the p-statistic. If I had been looking for a critical value, let's suppose that my alpha was 0.10. If my alpha was 0.10, perhaps because I'm using a small sample size, 10 in each group, and I chose 0.10 instead of 0.05, I would notice for 0.10 that the closest I can come without going over is right here at 0.09. However, there are 0.4s that are beyond this 0.09, so I cannot use 0.4 as my critical value. I'm going to have to go down to 0.5. Now I could use 0.5 as my critical value. My alpha prime would be 0.04, which is less than my chosen alpha of 0.10. Notice that I would use the exact same critical value if I had chosen alpha to be 0.05, but you can't do it after the fact, or you're not actually calculating correct probabilities. You have to make that decision about alpha ahead of time and then find out what your rejection region is in your critical value. Or as we did here, we went right to calculating the p-value, and once we calculate the p-value, we can see if it's less than or equal to our chosen nominal value of alpha. Now let's come to talking about me setting 0.5. We have to think about selecting pi 1 and pi 2 because the product binomial is about pi 1 equaling pi 2. And what I'm about to tell you now means that the product binomial test is not an exact test. Most of the tests that we've looked at in this video series on non-parametric methods are exact, but the product binomial test is not an exact test. We are looking at pi 1 and pi 2, and there are many possible choices. Anything that you choose for pi 1 and pi 2 to be the same, whether it's 0.4, 0.5, 0.7, 0.9, 0.34, all of those, as long as we hypothesize both of them for pi 1 and pi 2, the null hypothesis is going to be true. So let's think about reasonable choices. Let's let pi sub 0 equal that common value of pi. That is, pi 1 and pi 2 both are going to equal pi 0. And let's set it to 0.5. Well, it turns out that 0.5 happens to be for a Bernoulli event where you get the largest variance. And because of that, because of getting the largest variance there, that's the place where it's going to be hardest to reject the null hypothesis. So if we set the common value of pi to be 0.5, then we have a conservative test. That means that we're not going to exceed our type 1 error rate. It's not going to be an exact test, but we know that we can hold our type 1 error rate at under our chosen nominal value. Now, the problem with a conservative test is you might lose power. So there's another alternative that might make more sense. We can actually use sample estimates for that pi 0. How do we do that? Well, if we're assuming that pi 1 and pi 2 are the same value, that means that we can use every one in both samples combined in order to calculate that common proportion. So we can take the number of successes from the first sample, the number of successes from the second, divide that by the total in our samples, and that would give us our pi hat sub 0. So we've already used the conservative method, so let's look now at the other method. So if you look back at our table, you'll see that we had 8 successes in the morning and 4 successes in the afternoon. So 8 plus 4 in our numerator, and then we had 10 participants in each sample. So that gives us 12 over 20 or 0.6. So now instead of doing this distribution based upon 0.5, 0.5, I'm going to calculate it based on 0.6, 0.6. This does not guarantee that I will hold the type 1 error rate under 0.05, but it should give me values that are pretty close to the exact values. So it's really a payoff. Do you want to have a guarantee that you'll stay under 0.05 or whatever you set your alpha at, or do you want to kind of balance type 2 and type 1 errors and keep close to the correct type 1 error rate but get as much power as you can? So when we use this, again remembering that 0.4 was what we actually observed, you can see here that our p-value is now 0.108. So we're looking at a p-value that's a little bit bigger, or a little bit smaller, rather. The p-value that's a little bit smaller than what we had before, and that's what we would expect. Because if it's smaller, there's more of a chance that you'll get under that nominal alpha. In this case, we don't. But there's more of a chance for smaller p-values that they will be under our chosen type 1 error rate than for larger values. So that gave us a little bit more power, but didn't change the outcome in this particular example, but sometimes it could. Now, what about when we get large samples? Well, as with many non-parametric methods, if you get large samples, then you're going to have many different possible combinations. Really, you could go quite a ways with the product binomial if you think about the fact that you're just squaring the possible number of successes, assuming you have equal sample sizes. If not, you just have to multiply. You can go quite a ways with this, although you would probably want to write a function that doesn't show you the entire distribution, but just picks out for you what the p statistic is. But as n goes to infinity, the sampling distribution of delta hat becomes a chi-square with 1 degree of freedom. And we estimate the expectation of successes, because remember a chi-square is going to take observed minus expected. We estimate the expectations by taking the sample size times that pi hat sub 0, that is, using the actual estimate of pi sub 0 as our values, just like we did in the second example. And doing that for this particular example, which is not very big, and therefore this is not going to be a very good approximation, we ended up with p of 0.171. Quite a bit different than the p of about 0.11 we ended up with before. Which one should we believe? The product binomial, because the product binomial is getting us close to, not exactly exact values, but close to exact values. And the chi-square is based upon a mathematical distribution.